Hello, everyone, and welcome to this new webinar series, Science with QuEra, where we host QuEra scientists and collaborators to talk about some of their recent publications. And today, we have two scientists, Gefen Baranes from MIT and Harvard. Hi, Gefen.
Hi.
And Harry Zhou from QuEra and Harvard. Hey, Harry, good morning.
Morning.
And we'll talk about their paper, Fast Quantum Interconnects via Concentrate Entanglement Distillation. The Q&A box is open, so please, for the attendees, feel free to submit any questions you want, and I'll try to ask them of our scientists as we go along or at the end of the presentation. I'm going to start with a very brief introduction of QuEra and then hand it over to Gefen to get started with the real science. So QuEra, headquartered in Boston, close to Harvard and MIT. That's one of our superpowers, that we're friends with Harvard and MIT. We help customers tackle the hardest problems and help them make groundbreaking discoveries, and we do it with neutral atom quantum supercomputers that we're building. We believe that neutral atoms is the most promising quantum technology, and we know that QuEra is the leader in neutral atoms. So I think you've came to the right place. And we partner with enterprises, with high-performance computing centers, and with governments to form deep partnerships that help them achieve their goals. Today is a good day for QuEra. Earlier this morning, we announced a $230 million funding round led by Google and SoftBank and others. This gives us plenty of fuel to reach our goals of delivering true neutral atom quantum supercomputers with lots and lots and lots of high quality logical qubits. Why do we think that neutral atoms is such a promising modality? One reason is scalability. We and others have shown that we can pack lots and lots of qubits in a single machine. And so we don't need, certainly not up to at least tens or hundreds of thousands of qubits. We don't need optical interconnects that sometimes limit other modalities. Our neutral atom computer operates at room temperature. There is no need for the complexity and cost of cryogenic cooling, ideal for data center installation. Neutral atoms can be shuttled. In our architecture, we can move them around, and so any qubit can interact with any other qubit. And this allows us to create more efficient algorithms and implement newer quantum error correction methods. Neutral atoms exhibit high fidelity and long lifetime, coherence times of seconds, and they're natural qubits. They're perfectly identical. There are no manufacturing defects in atoms, and so we can put 1 million qubits, or one day we'll put 1 million qubits on a machine, and all these 1 million qubits will be exactly identical to each other. We're building computers, quantum supercomputers. Our first generation, Aquila, is an analog quantum computer that's available since November of 2022 on Amazon Bracket. 2.5 years later, it remains the only publicly accessible neutral atom quantum computer, and we're very proud of the work that our team has done with it, and even prouder of the achievements that many of our customers worldwide have reached fantastic research in simulation, optimization, and machine learning. And you're welcome to use it. If you've got a credit card and an Amazon Bracket account, you can use it this afternoon. Our second generation machine is built for HPC centers. It is a gate-based machine, at least 256 qubits. We're shipping one of these machines to the Japanese Institute of Science and Technology. Will be installed in the first half of this year, alongside a classical supercomputer. It's a very power efficient machine. You know, when people talk about supercomputers, they think megawatts. Here we require only a few kilowatts. And together with the machine, we provide installation, maintenance, and support, so that our goal is that in a couple of years, the customer looks back at the moment they signed a contract with QuEra and will say, this is easily one of the best business decisions I've ever made. So we've got a lot of work to get there, but this is certainly our goal. And we don't stop there. Here's a sneak peek. as much as the scientists allowed me to show of some of our third and fourth generation machines that we're building in our Boston offices. And with our new batch of funding, we invite you to join us for an unforgettable journey into the quantum future. As I mentioned, we are the leader in quantum error correction, and on this screen you can see some of the fantastic scientific work that was done, some led by Harvard, some led by QuEra, but always in collaboration, Harvard, QuEra, MIT. Most recently, we demonstrated logical magic state distillation. We've demonstrated pioneered algorithmic fault tolerance for fast quantum computing. And I think in December of 23, we published Harvard-led research about logical qubits, 48 logical qubits in various configurations that really created a little bit of a good earthquake in the industry, shifting the discussion from can quantum computers be built to can errors be corrected to, okay, let's now scale this to get to truly useful computers. Last, we don't do it alone. We don't believe that a single company can be the best at everything. So we formed the QuEra Quantum Alliance with best of breeds companies in algorithms, in deployments, in training, in many other disciplines, and we can bring this whole fantastic ecosystem to benefit our customers. And with that, Gefen, I'd like to turn it over to you for the meat of the presentation.
Thank you. Let me share the screen. Do you see the screen?
Yes.
Okay. So today I'm going to present to you, together with Harry, our project on fast quantum interconnects via constant rate entanglement distillation. You can take a look also on this archive. And I want to highlight that it's a joint work with Chris, Pablo, and Misha Lukin. So let's get into it. So the overview is the following. We're going to start with some motivation. Why do you want to use distributed algorithms, and our goal to get fast distributed logical algorithms? Now we're going to move to the approaches we use, which is constant rate entanglement distillation. Then we're going to discuss practical results in practical regimes and future research directions. So for the motivation, today we stand here. We have hundreds, thousands of physical qubits, and the error rates are around 10 to the minus 2, 10 to the minus 3. Now, to get large-scale useful quantum computers, we need to be right here. So we need millions of qubits, and the error rates needs to be much, much lower, let's say 10 to the minus 15. And we asked the following question: how can we make our computers big and to make them good with very, very high fidelities, meaning low error rates? So many people would tell you that the way to go is to go modular. So instead of building a huge machine with all of these qubits, we're going to build small units, independent units, and then we're going to connect them with some quantum interconnects. Now, this approach has many advantages. The first one is scalability, because economically, you prefer to manufacture many, many copies of the same thing and then connect them. Also modularity, because you're going to decouple all the challenges of the intranode and the internode. And finally, robustness, because you're going to be more robust for the failures at a given node. You know that you failed in this specific node, and it's going to be only local here, and you can fix it. Now, that sounds great, but why aren't we doing it and have like millions of qubits right now? Now, the problem is the challenge of the interconnects. So let's review. First, we have the local nodes. Imagine that you have a local quantum computer, and this will operate fast and with high fidelity. So if we look specifically on neutral atoms, we have many promising prospects. So our ability to control and move single atoms and perform single qubit and 2 qubit gates with high fidelity also allows us to have fast parallel control on logical qubits. Instead of physical qubits, we can control logical qubits. And also we can perform transversal gates between our logical qubits and use algorithmic fault tolerance to get to, let's say, 1 millisecond clock speed. Now, the problem is that the connection is way more faulty. Now, if you want to connect quantum computers, you need to create bell pairs. And these often involve physical photons. Now, these photons will be either in the optical regime or in the microwave regime, according to your architecture. And the problem is that these photons to generate the bell pairs using photons is going to be slow because photons are very, very lossy, and it's going to be noisy. So here are some examples of state-of-the-art experiments showing generation of bell pairs in atomic or ionic systems. And we can see that the rate of generation of these bell pairs is around hertz, hundreds of hertz. And the fidelities are around 95, let's say. So as you can see, we have slower bell pairs and noisier bell pairs than our gates on the local computer. So what we ask is that how can we address the communication bottleneck here that we have to get some fast and high fidelity logical algorithm that is distributed between multiple nodes? And the key idea here is that we want to use the local nodes abilities, these fast and high fidelity operations, in order to handle the noisy internode operations. So let's move into our approach. We want to use entanglement distillation. And what it means is that you're going to take some number m physical faulty bell pairs, let's say with error rates 10 to the minus 2, so 1%, and you want to distill them into some smaller number, k, logical bell pairs that have much, much higher fidelity. So the error rates, let's say 10 to the minus 12. And the key metric that we want to understand here is the bell pair overhead, which is how many physical faulty bell pairs do I need in order to get good logical bell pairs? What is this n over k overhead? And this is something I'm going to repeat during the rest of the talk, so keep this metric in mind. So there are promising approaches today in theory to generate these logical bell pairs. The first one is the 2EPP approach, where you use classical error correction codes to distill your bell pairs. And the other one is you can just make a direct logical gate between your two quantum computers, and in this work, they export the surface code or other topological codes. Now, here, in order to distill physical bell pairs 10 to the minus 2 to logical bell pairs 10 to the minus 12, the numbers that we're talking about are hundreds or thousands. It means that if each physical bell pair is slower, then the logical bell pair will be even slower. So it means that my logical algorithm will be slower. And this is something we want to take care of. So the results is the following. What we developed is entanglement distillation methods that will achieve asymptotic constant quantum communication overhead. So this overhead of physical faulty bell pairs to logical good bell pairs is going to be constant. And I'm going to explain in a second what I mean by this constant. And how we did it, we carefully select some code concatenation sequence using small codes that are quantum error detection codes. So this talk, as like the paper, we have 2 sections. The first one is the theory, where we're going to prove guarantees on a specific codes family to show you that we can prove that we have this constant rate entanglement distillation. And then we're going to go into the practical section when we're going to perform numerical simulations in practical regimes and show you our results where we achieve at least 10 times overhead reduction. So the setup is the following. We're going to assume that we have 2 quantum computers, let's say Alice and Bob, and each node has 2 sections. Section 1 is the computation section, when you have your logical qubit and you do the local gates between them with high fidelity. And the second one is the network section, where this logical qubit, all of their job is just to distill the bell pairs and make the physical faulty bell pairs into good logical bell pairs. Now you're going to transfer photons between these modules, and then you're going to get faulty bell pairs, and you want to distill them. Now we're going to use 2-way classical communication between these nodes, because it's going to allow us to use quantum error detection and post-selection. And then we can start with much, much higher errors for the bell pairs and we can distill them down to the number that we want, let's say 10 to the minus 12. Now, another important point to notice is that when we're going to get a physical belper in our link, we're going to inject it into some logical quantum error correction code in order to work on the logical level. And this will allow us to ignore all the local operations errors, and then we can use the communication channel way more efficiently. Okay, so what we're going to do is we're going to concatenate a series of quantum error detection codes, and we're going to take small codes, and each time we're going to increase the encoding rate of the code, such that the full encoding rate will go into the number that we want. Now, let's look at this illustration. Imagine that you start with these quantum error detection codes. You take N1 physical qubits, physical belpers, you distill them into some K1 logical belpers, and with some distance D1. So you're going to do this, and then the K1 logical belpers will go to the next step. And you're going to do it multiple times. You can do it in parallel. And then once you have enough belpers, you can move to the next step, and then distill more and more and get the logical fidelity to be the value. Now, here is a snapshot of the informal theorem that you can find in our paper. So we assume that we have some Pauli error on our belper, let's say P up to 50%, and we want to distill the belper into some error rate epsilon that can be arbitrarily small. Now, what we show you in this part is that the number of physical belpers that we need in order to distill K logical belpers with some error rate epsilon will be O of 1. Now, what do I mean here? Let's look at this illustration. So the y-axis here is this epsilon. What is the error rate of the final logical belper, which I want it to be very, very small. The x-axis here is the belper overhead, meaning how many physical belpers do I need to get final logical belpers with some error rate epsilon. Now here we can see the different curves for different sequences, where every point is a different code in your sequence. Okay, so as you take more and more steps in your entanglement distillation sequence, you have better fidelity, so the error rates goes down. But unfortunately, for some of these curves, also the physical overheads goes up. So here we can see in the dashed lines what's going to happen if you're going to use the classical codes. And we can see it's not constant because the overhead is increasing as I am decreasing the epsilon, the logical error rate at the end. But if we're going to use the quadratic parity code sequence that we use in our proof, we can see that we get the solid lines, meaning this line is just going down. And so this is the constant that I mean that you can distill and decrease the epsilon, the logical error rate of your final belper, without increasing the belper overhead. Okay, so now that I showed you the theorem that we choose a particular code family, and then we prove that we can get this asymptotic constant rate communication rates. Now I want to move to the practical regime, where we're going to analyze and optimize many, many code sequences to find the best one in some practical regimes. Okay, so what we did is that we choose a large set of codes. We can see here more than 500 sets of codes of different families. Also, I highly recommend these nice websites to find some code. And then we run the following optimization. We run a depth first search, a DFS algorithm, with the following constraints. We want the target output rate of the logical belpers to be 10 to the minus 12. We want some maximum 7 layers in our sequence. And then we also set some buffer, some memory size that we have in each quantum computer to do all of these operations. And I'm going to change this buffer so you can see for different buffer sizes. Now, the objective of the optimization is to return the code sequence with the lowest effective belper overhead. So let's look at the results. Here we can see on the y-axis the belper overhead, how many physical noisy belpers per one logical 10 to the minus 12 belper. And on the x-axis, we can see the buffer size, the amount of memory I have in each node in order to do these operations. Now, the different curves are for different error rates of the belpers. We can see from 0.1% up to 15%. Now, what is important to take from this plot? First is that as you increase the input error rate, you can see the colors becomes more bright. Of course, the distillation overhead is going to increase, but it's not significantly. And that's very important to understand when we perform these experiments. The second one is that you have this continuous trade-off between the input error rate of the belper and the buffer size. So you can decide to take a noisier channel, meaning the belper will have more errors, but then use more memory on each node in order to get the same belper overhead at the end and perform at the same speed when your logical algorithm. Okay, so now we can look at some comparison of numbers for the different approaches. So in the green one, I'm presenting the distributed logical gate between the nodes on the surface code. The yellow one is if you use the distillation, the 2-EPP sequence with classical codes, and then our approach is here in purple. So the different rows are for the different approaches. You can see the colors, and then the different columns are for different belper initial error rates, ranging from 0.1% up to 15%. So you can see that if, for example, we take a belper input error rate of 1% and we want to distill it up to 10 to the minus 12 error rate, you can see here how many belpers do we need in each approach. So what is really nice to see is that our approach is minimizing this number to, let's say, 6 belper. So you need 6 1% error rate belpers in order to get 1 10 to the minus 12 logical belper. Okay? So of course I should mention that there is a trade-off here between the module size, what is the size of each quantum computer that you have on each node, and the belper overhead. And that's like an interesting question to itself. Okay, so let me finalize with some applications for distributed quantum algorithms. So when we want to run an algorithm and it requires too many qubits that we need to distribute it between multiple nodes, we need to decide where we're going to make the cut, and then have two parts of the circuit, where let's say the upper part here is in specific quantum computer number 1, and the second part below the blue line is for a quantum computer number 2. So we can see that for different circuits, we can make the cut in different locations, and it also depends on the number of qubits in your circuit. So here we show you two examples of the ripple query adder circuit, where you don't need too many belpers per layer between the two nodes. As you can see here, the belpers that cross, the gates that cross the blue line. And there are other circuits where, let's say the random CNOT circuit, where you need many, many belpers all the time. And these are logical belpers after the whole distillation sequence. Now, this is just a hint for a much larger exploration area. But what we found is that in most relevant regimes, the communication will become the bottleneck when you want to run your algorithm in a distributed way. And this is why, if you're going to reduce the entanglement distillation overhead, you're going to have the key in order to run the whole algorithm in a much faster way. So this is why we think that our approach addressed this problem by reducing the belper overhead. So let's conclude. We saw that if we're going to use two-way communication, classical communication, together with a sequence of small quantum error detection codes that we're going to increase the rates, we're going to get this constant rate entanglement distillation at the end. And then we found that we can get orders of magnitude reduction in practical regimes. And this helps us to address the communication bottleneck in fault-tolerance distributed quantum computers. Now, this opens up many exciting research opportunities. Let me just highlight here 3 of them. The first one is that you can optimize the pipeline, and exactly to ask how do I perform each step in time, which steps are going in parallel, and which steps need to wait for the next one, and so on. The second one is to design it to specific hardware that you choose, for example, neutral atoms, and think about the parallel execution of your gates. And finally, you can think about compilation of large-scale algorithms, because there are many trade-offs to make here which, for example, one of them is that how large do you want each node to be? How many qubits do you want to spend on each quantum computer to do the computation? And how many qubits to do the networking? Because if you're going to give more qubits in your buffer to do the networking, the distillation overhead will be smaller. But then you have less qubit to do the local operations. So there is a large space here of interesting trade-offs to make. So finally, Harry and I would like to acknowledge the contribution of these great people, Chris and Pablo and Misha, and highlight that you should check out our archive right here. Thanks for listening.
Thank you very much, Gefen. What happens if you have a higher speed network? How do you balance the trade-off between memory size and network speed?
When you say networks, do you mean the rate of the physical bell pairs that I have?
The link between the computers.
Yeah, so higher speed network is good for us, right? Because then if we're gonna have physical bell pairs that are fast enough and the operations to distill them from physical to logical will be fast enough with small overhead, then we're happy. We're gonna have a fast distributed algorithm. So yeah, we do wish to have fastest possible physical bell pairs. And Harry can add.
Yeah, and I guess our techniques, because we search over all of these different combinations of the code sequences, we can really try to continuously interpolate based on this different trade-off space that we might want to navigate with future hardware.
And I see some questions on the Q&A chat. One question was, how many logical qubits did we use, at least in the simulation?
Yeah, so thanks for the question. Let's move to this slide. So here, when we say the buffer size on the x-axis, we mean in logical qubits. So here, these are 10 logical qubits that we use. And you can decide which quantum correction codes do you want to use. And this will set how many physical qubits you need.
Thank you. Harry, anything to add or any other questions that you saw of interest on the Q&A box?
There have been a couple of questions that I've been answering as we've been going through. Yeah, there are a few that I think, yeah, there's some questions about the achievable fidelity with this approach. In principle, we can achieve any fidelity. The fidelity, this overhead factor is for targeting any epsilon. So usually, as Gefen mentioned, the scaling with epsilon would be something like, I think, log 1 over epsilon, whereas here, the overhead would really be constant. Yeah.
I see another question on the Q&A. Is using atoms in cavities on both ends, that is increasing atom-photon coupling, does that improve error rates and fidelities?
Okay, I can take this question. So the multiple approach to generate the physical bell pairs between your nodes, and one of them, which is promising, is to use optical cavities. And then you have nice coupling between the photons and the atoms. So yes, this is an approach that people are going to try and are trying today in experiments. And there are nice theory works in the past 6 months that highlight that using this approach, you can get high fidelities and high rates. And yes, we wait to see it happens.
Wonderful. Any other questions from the audience? Anything that we should answer today?
Yeah, there's a question about transduction, which I think is a pretty interesting question here. One of the nice things about neutral atom systems, or in general atomic systems, or this also includes trapped ions, is that there are natural transitions that are already in the optical frequency, like as was also mentioned in the question just now. In fact, most of the manipulation of these atoms is already using light. And so in principle, some of these techniques can be demonstrated and developed in the next few years. And I think there's a lot of very active academic efforts really building some of these building blocks, increasing the rates, increasing the fidelities. So we're also excited to see what the community is able to demonstrate experimentally.
And as I mentioned earlier, we're also happy to look at interns or hire people to join this amazing team. So I think with that, let's conclude this debut of the Science with QuEra.
Thank you for the very nice presentation, Gefen.
Thank you. It was nice working with you.